Okay, guys, we're going to start talking about the symmetry of relations. Sometimes we're going to be dealing with functions, other times we're not. The basic idea is we're going to have some equations that we need to determine if the graph is actually an odd function or an even function. And before we get into that, we'll have to talk about what does it mean to be symmetrical. It's kind of like if you cut your body directly in half, you'll see that the human body, for the most part, is symmetrical. In other words, I have a right arm, and then on the other side of my body, a left arm. It's the same. Right leg and a left leg, they're the same. A right eye and a left eye, they're the same. For the most part, I get it. You can have all kinds of arguments. So here's the ideas that we have. The first thing that we see right here is we have symmetry over the x-axis. In other words, if I took this top graph up here and I fold it directly over the x-axis, then it would be exactly the same. The y-axis, or symmetry over the y-axis, it's the same thing. However, we're not going over the x-axis. Now we're taking this side and we're going to flip it over the y-axis, and it's the same thing as well. It's kind of like looking into a mirror is basically what the idea is. The toughest one to kind of realize would be axis over the origin. Now, the thing about that kind of makes it a little bit easier to understand, maybe easier even to see. If you'll take a line from one point right here on this graph, and you connect it to that point over there on that graph, which is kind of the same point, does it go right through the origin, or the point 0, 0? And if the answer is yes, then it has symmetry through the origin. So here's a few graphs right here, and let's kind of describe what kind of symmetry do they have, if they have any at all. And so out of the gates, what we have is we have a parabola that's going up. Now, it's not reflecting over this axis. It's reflecting over this axis. So if you took this side right here and you looked into the mirror, and the mirror was right here, then you could see that it is reflected over the y-axis. Going to the second one right here. This one's a little bit easier because we can see right here that it goes right through the center, and it's a straight line. So if I drew a line from this point to that point on the line, would it go through the origin? Obviously it would. So this one has symmetry through the origin. This graph right here a little bit different. You can see that nothing's happening over here in this quadrant, so through the origin is out. Nothing's taking place over here, so the y-axis is out. So if I took this side of the graph and I flip it right over here, in other words, the x-axis is now my mirror, then we see that this one has symmetry over the x-axis. Here's another one that we have that's kind of going through the middle. But could I draw a line from that point to that point? And you'd almost want to break out a straight edge right here, or an ID card or a credit card somehow to make sure that I'm not drawing my line perfectly straight. But that's pretty straight right there. Does it go through the origin? The answer is yes. So this one has symmetry through the origin. Take a look at this guy right here. Again, a little bit odd. But take a point right here. Take a point right there and draw a line. Now, I know I'm off a little bit right here, but if those graphs were drawn exactly right, we would see that it goes directly through the origin as well, from side to side right there. So this graph goes through the origin. Look at this graph. It doesn't go through the other side. It doesn't flip over the x-axis, but if my mirror was the y-axis right here, then that would be symmetry through the y-axis. This one right here is probably no different than this one right here, except for the fact that it's the negative parabola. So this also has symmetry over the y-axis. And then the last one we have right here is just a flip of the second one that we did. So we can see that this one goes through the origin as well. So we could come up with a ton of examples right here of how they're symmetric on a graph so that you could actually see them. But let's move on a little bit further and find out, when I'm only dealing with the equation itself, what do I need to do? So here's what we know. Odd functions are symmetrical across the origin. The key to this right here, because you're going to be asked this, you're going to be given a function, they're going to ask you, is it odd, even, or neither? So when we get the answers, which we'll go into, we need to be able to regurgitate this information in such manner. Origin starts with an O. Odd starts with an O. There's the idea right there. Okay, so odd functions, they're symmetrical across the origin. Even functions are symmetrical across the y-axis. Okay, so there's just a couple things that we're just going to have to get straight And how's that going to happen? Just through repetition. So here's the rules that we're going to follow. In order to determine if my graphs are odd or even, all we're going to do is we're going to solve the graph twice. Okay? Whatever the variable is, typically x, we're going to put a 1 in and solve it. Okay? And then after that, we're going to put a negative 1 in. We're going to solve it again. And what we find is that when the outputs come out, if the outputs are the same thing, then we know that it's an even function. As you recall from the last slide, the even function symmetric across the y-axis. If the outputs are opposite, the opposite would be 5 and negative 5, 3 and negative 3, 10 and negative 10. So two numbers that are the same, but one's positive and one's negative. If the outputs are opposite, then we know that it's an odd function. Opposite, odd. There's the idea. So now, what kind of algebra is actually involved here? All right, here's what we're going to do. First things first, let's put a 1 in for this function right here, and this is what we have. So when I put a 1 into the first one, I find out that the value of y is 5. Okay. Draw a little line under there. This math is not difficult, and everybody can do this. The second one that we have now is we're going to put in a negative 1 in for x and find out what we get here. Now, don't get this confused right here, but negative 1 squared, it's negative 1 times negative 1, which is positive 1. So look what we have here. So when I put in a 1 in the function, I get a 5. When I put a negative 1 in the function, I get a 5. So the outcomes are the same. And keep in mind now, when the outcomes are the same, then what do we have? This is an even function. Second one that we have right here, now we're talking about absolute value. Again, the technique that we're going to use is exactly the same. Put a 1 in for x. So here we go. The absolute value of 1 is 1. And where I went to school, 1 plus 2 is 3. So there's the first part. And again, we need to put a negative 1 into the same equation. And what do we find here? The absolute value of negative 1. Remember, whatever that number is on the inside, when we're doing absolute value, the output needs to be positive. So here again we have 1 plus 2 is 3. Now we see that our results right here are what? Just like the first one, they're the same. So this particular function is also even. Same idea. Let's see if we can get a different result here. Again, put a 1 in for x. 1 cubed, right? So 1 times 1 times 1. And we find that out to be 1. So there's the first part. Yeah, that's the easiest one so far, huh? I do the same thing with the other side, but I take a negative 1. So now it becomes this. Negative 1 cubed. Now negative 1 times negative 1 times negative 1 is negative 1. All right, so let's take a look at these two answers now. This answer is positive, and this answer is negative. Those are opposites. And because we have opposites in this case, this is an odd function. And the last one that we're going to do right here becomes our linear function. Again, plug a 1 in for x. So here's what we end up with. 3 times 1 plus 1 goes 3 plus 1. So the first time, put that value in for 1, we find out that y is 4. And do the same thing with the negative 1. And now let's see what we get. 3 times negative 1 is negative 3 plus 1. Now we find here negative 3 plus 1 is negative 2. So having a look at these two results, 4 and negative 2, they're not the same, obviously. 4 and negative 2, they're not opposites of each other. They're completely different answers. So this function right here is actually neither. So it's not symmetric to anything. So there's the math that's involved, and that's how we're going to do it. With that, hopefully there's no problems. Again, plug in a 1, get a result. Plug in a -1, get a result, then compare the answers, then apply it to the sheet that we had that told us if it's odd, even, or neither.